everybody. So it is a great pleasure to introduce Urtzi Buijs, professor at the University of Málaga in Spain. And we are very happy that he accepted our invitation to give this talk because we know he's very busy, not just with master students and research, but also with his YouTube channel, Archimedes Stuff, where he makes a real effort to support the popularization of mathematics, and videos are really great. So today he's our speaker, and he's going to talk about infinity structures in rational homotopy theory. So, go ahead.
Thank you so much. It's a pleasure for me to have been invited to this seminar, this virtual seminar. I would have preferred to be there in Seville, but well, next time it will be okay. I will share some slides. Let's see. I think this is the first one. So this is a kind of a course in rational homotopy theory and infinity structures. So rational homotopy theory is a subfield of homotopy theory, which has some intersection with differential geometry and also with higher algebraic structures. So I will plan to make some to show some examples in which higher algebraic structures arise naturally in rational homotopy theory. And then I will show some results of my research in the past and some of my research in the present. All of them related in some sense with these higher algebraic structures, infinity structures. And in fact, this homotopy theory this rational homotopy theory was the first example of Daniel Quillen of something bigger, which was called homotopical algebra. And this course, this seminar is oriented to operator theory. So I will speak about this intersection here in this picture. Well, more general, I will show some things, some classical things in rational homotopy theory, and also some results in infinity structures also. But let's start by the beginning, making some introduction to rational homotopy theory. So if we have a continuous map between simply connected CW complexes, then the following two properties are equivalent. The map induces an isomorphism between rational homotopy groups, and the map induces an isomorphism between rational homology. Such a map is called a rational homotopy equivalence. A space is called rational if its homotopy groups are rational vector spaces. And a rationalization of a space is a pair of a rational space and a map from the space to the rational space, which is a rational homotopy equivalence. So the study of the rational homotopy of a space X is just the study of the classical homotopy type of its rationalization. This rational homotopy theory is simpler in some sense, because, for example, if we have a finite simply connected CW complex, whose higher homotopy groups are the sum of some copies of Z and some finite groups, then the rational homotopy groups is just a vector space whose dimension is the rank of the fundamental of the higher homotopy groups. So I think this is a result. The first one is a result of Serre, and these things simplify a lot. In fact, rational homotopy theory is simpler because we have also algebraic models. And these algebraic models describe completely the rational homotopy type of a space X. Traditionally, we have these models in two categories: the category of differential graded Lie algebras. This is the approach of Daniel Quillen in the 60s, and the category of commutative differential graded algebras, which is the approach of Dennis Sullivan. Let's start with DGLs, differential graded Lie algebras. A DGL is just a graded vector space with a bilinear operation, which is with respect to the gradation, and satisfy that is the properties of graded antisymmetry and graded Jacobi identity. And we have also a linear map of degree -1, which is a differential and is a derivation with respect to the Lie bracket. Then Daniel Quillen showed a pair of functors between the category of simply connected CW complexes and the category of reduced DGLs, positively graded DGLs, such that it induced an equivalence between the respective homotopy categories, taking equivalences on the left as rational homotopy equivalences and quasi-isomorphism on the right, which are maps that induce isomorphism in homology. Then we can recover the rationalization of a space simply taking the model functor of the space and then the geometrical realization of this model. In general, we say that a DGL is a model of a space if there is a zigzag of quasi-isomorphism between the functor model of X and L. But among all the DGL models of a space, there is one which is particularly interesting, which is called the minimal Quillen model, which is free as a Lie algebra and whose differential has no linear term. We can read all the rational homotopy invariants of a space in terms of these models. For example, if we want to compute the rational homotopy groups of a space, then we take a DGL model, and the homology of this DGL model are just the rational homotopy groups shifted by one. For example, if we want to compute the rational homology groups, then we take the minimal Quillen model, and then the generators of this minimal Quillen model are just the rational homology of the space. For example, spheres are particularly simply described in terms of Lie algebras because the model of the sphere is a free Lie algebra with a single generator in degree n-1 and with zero differential. For example, products of spaces, Cartesian products, are described by products of DGLs. But here we have a drawback because this model is not a minimal Quillen model. And in this talk, I will explain at the end how to compute a Quillen minimal model of these Cartesian products, which is very interesting when we want to study, for example, topological complexity or to study polyhedral products, are very interesting for that reason. And wedge products can also be described in terms of minimal Quillen models, simply taking the generators of the two minimal models, and we have a minimal model of the wedge product. And for example, also, CW decompositions are very well described in terms of, I have avoided that, sorry. So let's continue with commuted differential graded algebras, the approach of Sullivan. A commutative differential graded algebra is a graded vector space, and in this case, we have a bilinear operation which satisfies associative and graded commutativity. We have also a linear map, but in this case, the linear map is of degree +1, which is a differential and a derivation with respect to the associative product. Also, Dennis Sullivan defined a pair of adjoint functors between the categories of nilpotent finite type CW complexes, where finite type is a space whose homology, rational homology, is finite dimensional in each degree, and the category of commutative differential graded algebras, augmented, finite type, and nilpotent. So there are more hypotheses there. We can also recover using these two functors the rationalization. Well, this also induces an equivalence between the respective homotopy categories, taking also quasi-isomorphisms of CDGAs, and we can recover the rationalization of a space also using these functors. And we say that a CDGA is a model if there is a zigzag of quasi-isomorphism between this model functor of X and the CDGA. We have also the notion of a minimal Sullivan model in this case, which is a free CDGA whose differential has no linear term also. And we can also read in terms of these CDGAs all the rational homotopy invariants of a space. For example, rational cohomology groups. We can recover the rational cohomology groups simply taking the cohomology of the CDGA. This is in some sense dual, Ekman-Hilton dual of the Quillen approach, because in that case, if we compute the homology, what we recover is the rational homotopy groups. But in this case, if we want to compute the rational homotopy groups, we take the generators of the Sullivan minimal model. So in this sense, this is dual. Everything is dual in between Sullivan and Quillen approaches. For example, the simpler spaces are the dual of a sphere is an Eilenberg-MacLane space, and in this case also it's modeled by a Sullivan minimal model with a single generator in degree n and zero differential. Also, wedge products in this case, which is the Ekman-Hilton dual of products, are described in terms of products of the CDGAs, and products are described in terms of the generators of two minimal Sullivan models of the factors x and y. So everything is dual between Sullivan approach and Quillen approach. So we have two pair of functors, one due to Quillen and the other due to Sullivan, but there are also some differences between these two approaches. First, the topological categories are different. In the case of Quillen, the spaces are simply connected, but they are not finite type. Finite type is not a hypothesis here. But in the case of Sullivan, he required a finite type condition, but he allowed the space to be non-simply connected, to be nilpotent. That means that we have a nilpotent fundamental group, and the action of the fundamental group on the higher homotopy groups is also nilpotent. But there are more differences between these two approaches. For example, the Quillen pair of functors is in fact a composition of 4 pair of adjoint functors. And also the Sullivan realization functor is simpler because it's defined as a co-representable functor co-represented by a simplicial CDGA. This contrasts with the Quillen approach. But in the intersection, if we consider simply connected finite type CW complexes, then these two approaches are related by a pair of adjoint functor that were described by Neisendorfer, which are the Quillen L functor and the Cochain functor. So we will come back to this pair of adjoint functors in order to see how L-infinity algebras arise naturally in rational homotopy theory. But let me show you one more example of a map of a space that can be described in terms of models. This is the study of function spaces. So these results were in my thesis, I think it was 15 years ago. And the goal of this study is to understand the rational homotopy behavior of mapping spaces, free and pointed, and the components. But we need some conditions on the source and the target, because first we need that x and y were finite type CW complexes in order to have a mapping space which has the homotopy type of a CW complex. Also require, this is a result of Milner, we also require that x and y are nilpotent. Well, in fact, I think that it's only necessary to have a target nilpotent in order to have a mapping space whose components are nilpotent. This is Hilton, Misling, Reuteberg. And we also require X to be a finite CW complex in order to have a component of the mapping space which is of finite type. In fact, we need to have a source which is compact in order to have that. But if X and Y are one-connected, are simply connected, we have not that the mapping spaces, the components are one-connected. So we need to work in the approach of Sullivan because we have all these conditions. So we have CW complex, which is nilpotent and of finite type. If we want to give Lie models, then we need to work in the intersection between Quillen and Sullivan approach, in the Neisendorfer approach. So let's describe a model for this mapping space. Take X and Y satisfying these conditions, X finite CW complex, and Y nilpotent finite type CW complex. Take a coalgebra model of X, and because this X is finite, then this coalgebra is finite dimensional, and we can take the dual coalgebra. but we take this coalgebra graded in the negative integers. So now take a Sullivan model of Y and then consider the following graded vector space, the tensor of the generators of the Sullivan model and the coalgebra. This is graded in the integers because we have things in negative degree in the coalgebra, things in positive degrees in the generator of the Sullivan model, so we can have elements in each degree. Take the free CDGA generated by this vector space. Then we define a differential here using the co-multiplication in the coalgebra and the differential in the Sullivan model. And this free CDGA with this differential is a model of the mapping space. Well, in which sense? Because this is not graded, this is not positively graded. In the sense that if we use the Sullivan realization of this CDGA, what we obtain is a non-connected space whose components are the components of the mapping space. But how can we recover the models of the components? Well, this is a result of Brown and Charba, but I think that it was also proved similarly by Heffliger previously. Take a model of a particular map from X to Y. Then we define a differential ideal generated by three sets: the elements on negative degrees, the differential of the elements of degree 0, and we identify the elements in degree 0 with some scalars. Then the projection of the model of the mapping space into this quotient space is just a model of the inclusion of the component of the mapping space into the mapping space, in the non-connected mapping space. And I also in my thesis show that this quotient CDGA can be described as a Sullivan algebra for some particular differential which is which depends on the phi of the model of the map F. Well, then, what about Lie models of this mapping space? So if we have DGL models of the source and the target, what can we do? Well, we can take a coalgebra model of X, which is just the Cartan-Eilenberg-Chevalley of the DGL-L, the DGL model of X, and we can take a Sullivan model, which is the cochain on L prime. Well, then we can now consider the graded vector space of linear maps from this Cartan-Eilenberg coalgebra to L prime. Here we have no structure, it's a vector space simply. We can take here the differential, the usual differential for any linear map. We can take this commutator of differentials, and we can define a bracket here, which is called the convolution bracket. We use first the co-multiplication and then the two linear maps F and G, and then the Lie bracket. And this defines a bracket which satisfies that is a Lie bracket, and the usual differential is a derivation with respect to this bracket. So this is in fact a Lie model of mapping space. How can we prove that? Simply checking that the cochain of this DGL is just the Brown-Charba model of the mapping space. And what about the components of the mapping space? Well, if we have a map, a particular map, and we have a CDA morphism of this map, then we can take, well, recall that this Sullivan algebra is just the cochain on L prime, and B is just the dual of the Cartan-Eilenberg-Chevalley. So the cochain on L prime is a free algebra, and this CDA morphism is determined by the linear map on the generators. So this is a linear map of degree 0, and if we take the dual of this, then the target is the suspension on L prime. If we desuspend this, we obtain a linear map of degree -1, which lives in our graded vector space of linear maps for Cartan-Eilenberg on L to L prime. Well, it's here. We can now define a new differential perturbing the original differential by the adjoint of this element. But this is a differential if and only if the degree -1 linear map satisfies this equation, which is called Morgenstern equation. So we can now consider the vector space truncated in negative degrees, taking the kernel in degree 0, and this DGL, which is positively graded with the perturbed differential, is in fact a Lie model of the components. And this is showing that the cochain of this DGL, truncated DGL with the differential perturbed, is just the free CDJ, what we have seen that is isomorphic to the quotient model of the component. So everything about rational homotopy theory. And I want to introduce now L-infinity algebras in rational homotopy theory. So let me change that. I have to share the second part of the talk, which is this one, I think. Yes, I think. Recall that we have this pair of adjoint functors due to Neisendorfer from CDJs to DGLs, and then we will associate to a DGL a particular CDJ. So recall that we have DGL, which satisfies gradient antisymmetry, graded Jacobi identity. The differential is a derivation with respect to the Lie bracket, and we will associate to this DGL a free CDJ. But this will not be a minimal Sullivan algebra, because the differential of this free CDJ will have linear and quadratic part. In order to define this linear and quadratic part, first we take the generators of this free CDJ as the dual of the suspension of L. Then now we have a pairing, and we can define D1 in terms of the differential of the DGL using this pairing. We can also extend this pairing to this map and define D2 in terms of the Lie bracket in this way. So we have defined these two parts of the differential, D1 and D2, but we have to check that this is in fact a differential. So we have this by distribution, we have these four terms. Well, D1, D1, these live in the generators of the vector space. These two terms live in the word length 2 elements of the CDJ, and this lives in word length 3 elements in the CDJ. So if this sum is 0, all these three terms have to be 0. So the first one is 0 because we have a differential in the DGL. The second one is 0 because this differential is a derivation. And the third one is 0 because we have Jacobi identity. But it seems that it's not necessary the graded antisymmetry, but it is necessary in the definition, because these two things, this is graded antisymmetry and graded commutativity, is used here, because we have that if we replace the bracket by the antisymmetric bracket and this D2V element by the commutative element, the qualities should hold also. So this is used here. So let's check this equality, because really interesting. This deserves to be done for everybody who is interested in studying rational homotopy theory. For example, how can we translate these two things? Why these things are equivalent? Well, D1 is 0 if for any element V and X, this pairing is 0. But we can now apply the definition of D1 and apply again the definition of D1, and then we obtain that this is 0 if and only if this is 0. Let me show you the second identity of this definition. We have to see that this is 0 if and only if the differential in the DGL is a derivation with respect to the Lie bracket. So, well, let's start with the second term. This is 0 if and only if this extension of the pairing is 0 for any element v, x, and y. But this is applying the definition of D2, this element. So we have the first, well, apply now the definition of D1, and we have this first equality. The first term is hard to work because first we have to use that D2 of V is an element of word length 2. And now recall that D1 is a derivation with respect to this associative product. Now we split this in two parts and recall the definition of this extension of the pairing, which has these terms. Now apply the definition of D1. And now we switch these two elements and see that the first line is just this thing, and this thing is the second line. Recall that the product of U and W is D2 of V, and then apply the definition of D2. We put these things together, and now if we sum these two equalities, what we obtain is that this is 0 if and only if this is 0, which means that the differential of the DGL is a derivation with respect to the Lie bracket. So the third identity, which is D2, 0 equals the Jacobi identity, is also very interesting, but I will not do here. So why, if we replace the notation, the bracket we write as L2, this is a linear map of degree 0 from L tensor L to L, and this L1 by a linear map of degree -1 from L to L, we see that we can write here more linear maps of degree k-2 from the tensor product of k times L to L. And then this could be related with a Sullivan algebra with word length of any degree. Okay, but we need to have some definition here. We define an L-infinity algebra as a graded vector space with a family of linear maps of degree k-2 satisfying two conditions. First, we need a graded higher antisymmetry. And second, we need a generalized Jacobi identity. And with this definition, we can also extend the cochain functor and obtain a differential with all the terms. How can we do that? First, we need the graded antisymmetry, generalized antisymmetry, in order to define the dk term of this differential by analogy of what we have done in the previous cases. And here we need that because to have that here and here can be changed, and this should be well defined. And then we need the second identity in order to have a differential, because here we have more terms. We have all these things. So first we have D1 should be 0. This involves only the first bracket. We have D1, D2, D1 equals 0, which involves the first two brackets. But here we have not D2 equals 0, because here we have more terms. If we write this thing in terms of the L-infinity, what we obtain is the following identity. And this part is Jacobi, but we have more terms because we have here a three bracket, L3. So this is the definition of L-infinity algebra in terms of the cochain functor and Sullivan algebras. In fact, this is not really general because the differential on the Sullivan algebra should should we well define it? It should be a finite sum, and there are some restrictions, and we have to impose some restriction also on the L-infinity algebra. So the most general definition of L-infinity algebra in terms of free objects is this one. An L-infinity algebra can be seen also as a codifferential in the cofree coalgebra generated by the suspension L. And we have also in this term, or the definitions of infinity structures, for example, an infinity algebra is a codifferential in the tensor coalgebra on the suspension of A. And we can also define a notion of infinity algebra, of C infinity algebra, an infinity commutative algebra. Well, this can also be written in terms of a family of linear maps of degree -2 which satisfies some identities. And we can define a C-infinity algebra to be an infinity algebra whose higher products vanish in the shuffle products. In the same way, we can also define a notion of A-infinity coalgebra, which is a differential in the tensor algebra under the suspension of C. This can also be described in terms of a family of linear maps, a family of higher comultiplications, which satisfies some identities. And we have also the notion of a C-infinity coalgebra, which is an A-infinity coalgebra such that the image of the commultiplication in degree of K commultiplication vanish on the unshuffled product. But this can also be described in terms of freely algebras, because a C-infinity coalgebra is just a differential in the freely algebra generated by the suspension of C. Because this can be seen as a sub-Lie algebra of the tensor algebra with the commutator product. So in fact, the freely algebra is the less Lie algebra which contain all the generators in the tensor algebra with the commutator bracket. We will go back to this interpretation of C-infinity coalgebras in the last part of the talk. So, why these L-infinity algebras appear in rational homotopy theory? The first time I found these L-infinity algebras was in the context of the rational homotopy function spaces. Recall that we have a CDJ model of the source and a Sullivan model of the target. We have a Brown-Sharpe model. Well, but this Brown-Sharpe model was defined for any Sullivan algebra, not only for one which has a differential with linear and quadratic part. So if we have such a Sullivan algebra, how can we define something whose cochain is this Brown-Sharpe model? In this case, we have that the Sullivan model is the cochains on an L prime, which is not a DGL, which is an L-infinity algebra. Oops. This one. So this complex of linear maps from the coalgebra to L prime will not be a DGL in this case. This will be an L-infinity algebra in order to have a differential with D1, D2, D3, and so on. But how can we define this structure of L-infinity algebra in this complex of linear maps? Well, let's see. First, the differential is the usual differential, but in order to define here a higher bracket, we use the iteration of the commultiplication. So this is not the structure of infinity coalgebra. This is simply the iteration of the coproduct, and it does not depend the order because it's co-associative. So then, to describe the model of the components, if we have a particular map from X to Y, this gives an element of degree -1, as we have seen before. But is there a notion of Maury-Cartan element here in L-infinity algebras? Yes, in this case, it's this equation. So if we have a map, then this map gives rise to a Morgenstern element, and we can perturb not only the differential, as in the case of the DGLs, but only all the brackets in that way, where we have here J times the Morgenstern element. And with this perturbed differential and higher brackets, this is an L-infinity algebra, which is a model of the component of the mapping space. Simply writing here the differential and the, not only the differential, also the higher brackets are perturbed with this formula. Okay, this is how naturally arise L-infinity algebras when one studies mapping spaces. But I will show now a tool which is particularly important in, well, let's see, in, oops, let me see. A particular tool in higher structures, which is called the Homotopy transfer theorem. Let me describe what this theorem said. We consider two complexes, then a contraction between these two complexes is three linear maps satisfying that H is a homotopy between the identity on A and the composition of P and I is a quasi-isomorphism of complexes. So we have a homotopy retract, we can transfer infinity structures from A to V. Let's see how. And this can be done explicitly also. We denote TK, the isomorphic classes of directed rooted trees, and PTK, the set of isomorphic classes of planar rooted trees. So for example, for T3, we have two trees, but the planar trees, we have three trees because we can take one outside of the plane and put like that. So now we will define some linear maps. First, for example, for this tree, if we have an infinity coalgebra, we will define a linear map from the tensor product for C to the tensor product of K times C in the following way. If we have a retract, we do the following thing. We label all the internal vertices by the higher coproducts. We label the leaves, the root of this tree by I and the leaves with P. So we read now this tree, and the internal edges by the homotopy, from the bottom to the top. And this gives a linear map from V to V times K. We do the same thing for an A-infinity algebra, but in this case, we label the leaves with I and the root with P. And we read this tree from the top to the bottom. And this defines a map from V tensor K to V. And also for L-infinity algebras, we can also define a linear map, in this case, in the similar way, going from the top to the bottom. But in this case, we need to compose this map with the symmetrization. Well, then we have what say the Homotopy transfer theorem. The Homotopy transfer theorem say that if we have an infinity coalgebra, then we have a contraction, then there exists an infinity coalgebra structure on V and an infinity quasi-isomorphism between both infinity coalgebras, such that the first of these infinity structures in V is just the differential, and the first of this family of maps is just the quasi-isomorphism of complexes. And this is described as the following sum on all the linear maps that we have defined. The same thing can be said for A-infinity algebras in a similar way, with a sum over the trees of the linear maps defined by the trees, and also for L-infinity algebras. How can we use this homotopy transfer theorem in the study of mapping spaces, or in general of rational homotopy theory? Let's see. Suppose that we have a DGL model of X and we want to compute a Quillen minimal model. We can do the following thing. Take a supplementary of the kernel of the differential. And then the differential of this supplementary lives in the kernel, so we can take a complementary of this image of M. So we have this isomorphism because M is not in the kernel, and we can show simply that this H is just isomorphic to the homology of L. Then we can define the following contraction of this DGL into its homology. Then we can transfer the DGL structure on L to an L-infinity structure on H, which is the same thing as a differential in the free commuted CDGA over the dual of the suspension of H. And this is just the minimal Sullivan model of X. The same thing can be done for Quillen minimal models. In this case, if we start by a coalgebra model of X, then we do the same construction. We write this as a sum of M, the differential of M, and something which is isomorphic to the homology of the coalgebra. This defines a contraction between the coalgebra and its homology. Then we can transfer the coalgebra structure into an A infinity, in fact, a C infinity coalgebra structure. Because if the coalgebra is co-commutative, then the infinity structure transferred is also C infinity. Then we have here a C infinity coalgebra, which is the same as a differential in the free Lie algebra generated by the suspension of H. And this is just the minimal Quillen model. Then we can use also this construction to give a model, an L-infinity model for mapping space from X to Y, whose underlying vector space is the linear maps from the rational homology of X into the rational homotopy groups of the loops of Y, the target. How can we do that? First, start with a coalgebra model of X. Then we have a contraction, as we have seen, and we take a Sullivan model of the target. Recall that if we take L, the suspension of the dual of this is an L-infinity model of Y. This is an L-infinity algebra such that the cochain on this L is just the Sullivan model of Y. So this L is just the rational homotopy groups of Y shifted by 1, so the loop of Y. And take now the functor linear maps to L into this first contraction. So we obtain another contraction, but recall that we have endowed this linear complex of linear maps an L-infinity structure, which was an L-infinity model of the mapping space. So we can transfer this into an L-infinity algebra and recall that H is just the rational homology and L is just the rational homotopy. So we have done. This L-infinity structure gives a model of the mapping space. So this is everything about L-infinity algebras, but I don't know if I think that I have some time to show a problem which I'm working now, which is the study of the Cartesian products, minimal Quillen models of Cartesian products. Let's see this one. Recall that we have said that if we have two spaces, X and Y, then we have two DGL models, then the product of these two DGLs is a model of the product. But this is not minimal. So we can obtain a minimal Quillen model of the Cartesian product starting from minimal models of the factors. How? Well, we can take the following quasi-isomorphism showing that this is a minimal Quillen model of the product, where phi of V is V, phi of W is W, and the phi of these elements, which are the suspension of the tensor product of the generators, is 0. And the differential of this model is defined in the following way. The differential in each V and W is the same as in the models of the X and Y. And the differential of an element of the suspension of the tensor product is the bracket of V and W plus something which is in the kernel of this quasi-isomorphism. Let's see with some example how this, well, this was in the book of Daniel Tenre, but this gives the existence of a free Quillen model and how it is, but this is also a procedure to obtain this model. But this is not a formula. In fact, this procedure could be hard and lengthy, so the goal of this part is to find an explicit definition of this differential of this model of the product. Let's see some examples. First, products of spheres. Recall that the model of a sphere has a single generator in degree n-1 and degree m-1. So then the model of the product is just a freely algebra with 3 generators. And the differential of V and W is 0, and the differential of this element is the bracket. And this is the model, because we can check that the square of this element is 0 because the differential of V and W is 0. So this is the model of the product of 2 spheres. This is the only example which is really simple, because, for example, if we complicate the things a little bit and we take a complex projective plane whose model has 2 generators and the differential of x 0 and of y is the bracket of x with itself, and we take y to be a sphere, then a model in this case is given by this freely algebra. The differential of this is the same as in the factors. The differential of this suspension is the bracket of V and X. But if we define this like that, this is not a differential, because in this case, the square of this element, this is a derivation, so the d of V is 0, but here d of y is the bracket of x and x. So we have no 0 here. How can we add more things to this differential in order to kill this term? Well, we can apply here Jacobi identity and antisymmetry, and then see that this element has differential the bracket of V and X. So if we add here this element, then now the differential is 0. And this element is the element that beta of V and W, this element will live in the kernel of the quasi-isomorphism. So this should be done by hand in each case. So these are examples. But there is only one situation in which we have seen a formula previously, which is in the case in which X is a coh space and Y is any space. Let's see. A coh space rationally is a wedge of spheres, and its model is simply a freely algebra with 0 differential. So if we have a Quillen minimal model with 0 differential and any other Quillen minimal model, then the product can be described by this formula, where this sigma V is a derivation, which on a generator is simply sending the element to the suspension of V at tensor W. Okay, let's see why this is that was done by Lupton and Smith. Let's see why this is a differential. Well, first, this can be written also as sigma V. So we write that. And this bracket can be written as the adjoint of V on W, which is a derivation. Okay, now let's see how can we prove that. There is an order in the elements of a basis on a freely algebra, so we can prove that by induction. If we see that this formula is well defined for all the elements of degree minus than I. So this the adjoint of V can be written in that way in this freely algebra. Then we can use this to see that this differential, the square of this is 0. Let's check. First, we apply that D is a derivation and the differential on V is 0. So we jump here, and the differential on W is the differential on V on the factor. And now see that this element lives here. So we can apply the definition of the adjoint and replace here in that way. So we simply check now that these two terms cancel, and we have here the square of a differential. So we obtain 0, and it's done. So we want to generalize this construction because, well, a QH space is a space which is really simple. Can we do something more general? For example, well, this is the relation with infinity structure, because this problem can also be read in terms of C-infinity coalgebras. And the problem is the following. If we have two C-infinity coalgebras, can we endow the tensor product of these two vector spaces with a C-infinity coalgebra structure such that it extends the one in C and in H and H prime, satisfying these two conditions? And we can see that this by the the equivalence between a C-infinity coalgebra and the differential in a freely algebra, we can see that this, in fact, well, I will go fast here, that this is equivalent to the problem of finding the differential D in the product of the model of Tanre. Right. So let's see. So we write this in that way. Oops. This is V, this is W, and this is isomorphic to the suspension of V and W. And this condition on the infinity C and the C-infinity coalgebra are just the conditions on the problem of Tanre. So it's the same thing. So we can reinterpret the problem of finding a model, a free Quillen model of the Cartesian product in terms of endowing a C-infinity coalgebra structure on the tensor product. But let's see what have we proved. If we have two spaces which are two cones, which are spaces that have a decomposition of the generators such that we have elements whose differential is 0 and elements whose differential goes to the freely algebra of the previous one. So in this case, we can define here a differential. Here is the differential that we know. Here we have the differential, simply the Lie bracket. Here we have the situation of the Lupton-Smith model. Here also. So the problem is to find the differential for these elements. And we found that we can define it adding the two terms of the Lupton-Smith model plus something which is called the star product. But I don't know if I have enough time to show a little bit how this star product works. I don't know, Maritania, if I have time.
Well, it is. You have a couple of minutes, let's say.
Okay, I will see quickly this thing. This was done. This is a joint work with Carrasquel and Lucille van den Broek. Let's see how this differential works. This star product works. If we have two elements here, which are there is a brackets of elements, I will write this define this star product in terms of trees. And we write this tree for these brackets. So, and if we have a bracket like that, this will denote the over a tree. This will denote the derivation of sigma v over this bracket. Okay, where recall that this derivation in an element was a suspension of the tensor product. So this. Let's see. Well, if we have instead of a generator, we have a tree over a tree. This is this derivation, which is defined simply changing this thing like that. So the definition of this star product is the following thing. We define a a tree which is simply a branch tensor, a tree is 0. And if we have a tree which has a bifurcation, then we define this inductively following this formula. So, well, I have put an example here for that, but maybe I will need more time. But it's thing like that. You apply here first this, which is the derivation 2 times, and then the first is 0 because t prime is a branch, and this is not 0, and it's something like that. But well, in fact, this is a kind of generalization of Lupton-Smith derivations, but instead of derivation of a single element, it's a derivation of trees. But okay, I will stop here because I will. This is a little bit technical to be written. So I stop here.
Okay, so thank you for the talk. And okay, so are there any questions or comments for Urtzi? No, Fernando. Yes, Fernando has one question. Go ahead.
Hi there.
Hi,
How are you doing? Well, that is my question. But I wanted to ask you, it's a general question, right? Have you ever found, doing this kind of mathematics, differential graded algebras over things which are not the rationals, like saying like the ring of power series on one variable or several variables of the rationals? Like to model, I'm thinking of modeling families or parameterized families of rational homotopy types or sheaves of rational homotopy types.
Yeah, I have not done that really. So I know that this thing is related with deformation theory, and we had in the past some project of doing deformation theory in terms of DGLs, but I have not gone that way. So I really don't know exactly.
Okay, and all these three models, since they are free, they are huge, right? They are far from being finite dimensionals, unlike the Sullivan models.
Yes. They are more problematic because we have Jacobi identity. We have no commutativity. And then things are really huge to compute. In fact, it's difficult even to give a basis as vector space of a free Lie algebra. So you have some, I think that what's the name? Hull basis to describe these free Lie algebras. So Fernando has gone.
That we had some trouble with connection. Are you there, Fernando?
I'm back. I don't know what happened.
Yes,
I was asking whether, I mean, how do you deal with these huge algebras? Because they are far from being finite dimensional, and bases are complicated to compute.
Yeah. This is what I was telling, that even the basis of as a vector space is really complicated. You have this, I think it's whole basis. I don't know if you know this book of, I think it's Reutenauer, which is called Free Lie algebras.
Really?
This book is dedicated to this thing, to free Lie algebras, a whole book, and it's really complicated. This is the reason why it's difficult to find, even for simple cases, a differential in the model of the product. But it would be nice to have this differential, because it's true that you need to make a big effort to describe these models, but you can obtain important consequences. For example, one thing that you can prove really easily is that polyhedral complexes, if X is a formal space, then polyhedral complexes are formal spaces. And simply because a formal space has some minimal Quillen model whose differential is quadratic. Then you can see that this differential on the product is quadratic also if the differential of D is quadratic. And then you can obtain a model of the polyhedral product simply removing some generators. So your model is also quadratic, and then they are formal spaces. And if you use Sullivan tools, it's more complicated to prove that. So I think that if we can found these formulas, then we can obtain some important applications.
Okay, thanks a lot.
So any other question? A comment or no? Okay, so thank you again.
Thank you.
And yes, so see you next week, next
Perfect.
Tuesday at 4 p.m. with our last talk. Okay.
Okay. Bye.
Bye, thank you.
See you next time in Seville.
Bye.
Adiós,
Yes.
Fernando.
Pronto espero. Chao.
Ojalá. Chao.
Bye.
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 Chao, Urtzi.
Adiós, Ramón. Bueno, pues ya está.
Víctor, ¿estás grabando? Creo
Sí.
que, bueno, ya sabrá, no sé, Víctor se ha ido, yo creo
Ah,
que
no,
ya.
ahora pone la grabación se ha iniciado. Creo que si tú la has dado,
Yo le he dado a
que
descartar.
porque tú le había apagado y tú la has dado y se ha empezado a grabar de nuevo. Pone, la grabación se ha
¿Está
iniciado.
grabando? Qué
Sí.
raro, yo le he dado a descartar. Bueno, si está grabando algo, luego lo cortamos. ¿Eh? No sé, yo le he dado a descartar a una cosa que ponía, pero no. Bueno, pues nada, muchas gracias.
Pues nada, hasta luego. Hasta la próxima.
Venga,
Chao.
hasta luego. Adiós.